Okay, so electric potential difference is defined as a ratio of the work needed to move a charge to the magnitude of that charge. It is a scalar quantity, that means it does not have direction, it has only magnitude, and its unit is volt, represented by the letter V. Now there are different formulas for electric potential difference. The first one is work done per unit charge. Delta V is equal to work done per unit charge. So this delta V is the symbol for electric potential difference. Work is represented by W, and Q, we know that it's charge. There is one more formula which we can use. Instead of W, we can write delta U, which is electric potential energy. And in short form, sometimes you will see it as written as EPE, electric potential energy. For uniform electric field, we can actually derive another formula from these two formulas, and that comes out as delta V equal to ED, and we are interested in the final formula, delta V equal to ED, where E is the electric field and D is the distance. Now if you want to know how we got this formula, you can check these two steps. This is the formula for electric potential difference, where we replaced work done by FD, W is equal to FD, and electric field itself is given by F over Q, which we learned in previous classes. So when we combine, or when we rearrange these two, we can get the formula for delta V, electric potential difference, as ED. So delta V basically has three formulas which we need to get from this slide. W over Q, delta U over Q, and E times D. Now electric potential or voltage, so let's just write this as electric potential difference or voltage, can change according to whether you are bringing the charges closer to each other or you are moving the charges away from each other. So if you have unlike charges, unlike means different charges, so like in the first diagram we have got one negative and one positive. If you move them apart, so the distance between them is more here, so you have moved them apart. If you move them apart, then the electric potential difference is positive, said to be positive, and that's a case of high voltage. High V means high voltage. Voltage is another name for electric potential difference. If you move the unlike charges closer to each other, like in this case, then that's a case where you have electric potential difference to be negative, and that's the case of low voltage. Now we can also see in the second diagram, that's about like charges. Like charges means you have similar charge, positive, positive. If you bring like charges closer, then that's high voltage, and if you take the like charges far away from each other, that's low voltage. Now in the same way, we can think about electric potential energy. We can increase or decrease electric potential energy. We saw electric potential energy in the formula for V equal to delta U over Q, or let's say delta V equal to delta U over Q, where this delta U is the electric potential energy, electric potential energy, and delta V is the electric potential difference. Just now we saw in the beginning of the video. Okay, now if we want to increase electric potential energy, this EPE is short form of electric potential energy. So we can think of increasing electric potential energy or decreasing electric potential energy. There are different ways to do it. If you want to increase electric potential energy, then you have to bring the like charges closer to each other. Okay. If you want to decrease electric potential energy, you have to take the like charges away from each other. So if you want to draw this, let's say if you want to draw this, so if you have two positive charges and if they are closer to each other like this, their electric potential energy will be more. But if I take two positive charges and if I keep them away from each other, they are like charges because I've taken both of them positive. If I keep them away, means the distance between them is increasing, so electric potential energy will be less or it decreases. If you take unlike charges and keep them closer like this, unlike means one should be negative, one should be positive. If you keep them closer, then the electric potential energy will be decreasing or it will be less. And if you keep them away from each other, then the electric potential energy will be increasing. Okay, so that's a table which we have to remember and memorize. You can actually think about, like, if you bring like charges closer to each other, they are going to repel. So if you have to keep them together, you have to spend more energy to keep them together. So if you want to keep two positive charges together, you have to spend more energy to keep them together, and therefore the electric potential energy will increase. In the same way, if I have to keep unlike charges away from each other, you know that they would naturally attract. But if I want to keep them away from each other, we have to do more work to keep them away from each other. That means their electric potential energy will increase. And the opposite will happen when you are trying to decrease the electric potential energy. Now let's talk about equipotential surfaces. Equipotential surfaces are the surfaces which have same electric potential. Okay, so the electric potential difference between two or more positions is zero. And such a surface will be called as equipotential. Equi means equal. So equal potential. So the surfaces on which the potential remains the same. For example, here in this picture I have got a positive charge in the center. There's a positive charge in the center, and around it there are some circles. Okay, so on the first circle it is written 10.6 volt. So if I take any point, let's name A, B, C, as long as these points A, B, C are on the same circle, their potential will be 10.6 volts. So the potential at A is 10.6, B is 10.6, C is 10.6. So that means they are on an equipotential surface. And the potential difference between A and B will be zero, because they are on the same potential. Similarly, if I take, let's say, a point here D and a point here E. Look at D and E, they are on the second circle. The potential there is 7.4 volt. So potential for D is 7.4 volt. Potential for E is also 7.4 volt. So they are said to be on equipotential surface. And if I want to take the difference between them, if I do VD minus VE, that will come out as 0 volt. So that's what it says here. Potential difference between two or more position is 0 on an equipotential surface. Similarly, we can see for a negative charge. So for a point charge, equipotential surfaces are circular in shape. These are some examples for a single point charge. The red color line which you see, these are the equipotential surfaces or equipotential lines in both the cases. So this is for a point charge, and this is for if you have plate of charges. Like for example, on one side you have got positive charge, positively charged plate, and on the other side you have got negatively charged plate. So in that case, the electric field lines will be from positive to negative, which we know from the previous class, and the equipotential lines or surfaces would be perpendicular to these electric field lines. Now if you, again, this is to bring back the same concept, if you have a positive plate and a negative plate, electric field lines will be from positive to negative. We just want to add this particular word here, like instead of saying positive plate, we can also call it as high potential, and the negative plate can be called as low potential. So electric field always points from high potential to low potential. Okay. Electric potential is higher near the positively charged plate and lower near the negatively charged plate. And the magnitude and direction of electric field, you can see all the lines are towards the right. So the direction is same as well as the magnitude. That means if I take any 2 points, let's say a point A here and a point B here, electric field at A will be equal to electric field at B. That's why we call it as uniform. That means same electric field lines or same strength of electric field. This is true only for two oppositely charged parallel plates. Okay. Now let's copy that here. So delta V equal to ED, I'll have to write that again. D is 1.5 centimeter, which is 1.5 into 10 to the power negative 2 meters. We have to convert that into meters, and E is equal to 1800 Newton per coulomb. So we can write that 1800 multiply 1.5 into 10 to the power negative 2. And I'm just going to use my calculator here. You can also check with your calculator. That comes out as 27. Let me just confirm once again. Yeah, that comes out as 27, and we are calculating electric potential difference, so the unit will be volt. Next is asking how much work is required to move a proton from negative plate to positive plate. So now we have to talk about, or we have to find out, what is W. So if you remember, we had different formulas, 3 different formulas for delta V, out of which one we already used here. There was one more formula, delta V equal to W over Q. So W will be equal to Q times delta V. Delta V we have already here 27, and Q is for proton. So for proton, the charge for proton is 1.6 into 10 to the power negative 19 coulomb. You can see that it's not given in the problem. It's a universal constant. We need to know it. Okay, or it will be provided in the exam. So 1.6 into 10 to the power negative 19 multiplied by 27. Again, we can use our calculator, and that comes out as 4.32 into 10 to the power of negative 18. And because we are calculating work done, the unit will be joules. So that's how we can complete this sample problem. Now in your notebook, I want you to finish the independent problem, so that if you have any problems, you can discuss it in the class. Okay.